Hello, welcome back to the discussion on quantum optics. So today we are going to discuss a very simple model to describe the atom field interaction quantum mechanical. So this model is particularly known as Jaynes Cummings model, and in short it is called JCM. Okay, so Jaynes Cummings model is a fully quantum mechanical model to study the interaction between a single mode field and a two-level system. Okay, now what is meant by a single mode field? Okay, so we know that in practically we cannot get a single mode field. It is very difficult to achieve the condition for single mode field. A single mode field means a field with a single frequency, single polarization, and single direction of propagation. So it is very difficult to achieve the single mode field. But now we have the experimental methods to achieve to confine a single mode field inside the cavity. Okay, so although the field contains many possible modes, so it has recently become possible to make cavities which supports almost only a single mode. Okay, and similarly if you look at atomic system, so atomic system in general may have many possible energy levels. Suppose if you take hydrogen atom, so hydrogen atom can have different energy levels. Its lowermost energy level has the principal quantum number 1, then n equal to 2, n equal to 3. So we have different possible energy levels. But now it is possible to control the transition between these atomic levels. So if you can able to restrict the transition between only two possible levels, then that system act as a two-level system. Okay, so in fact the atomic system in general have more than two possible state. So with the recent technology it is possible to confine transition only between two states of an atom. Okay, so such systems we can call a two-level systems. Okay, so basically what we are going to study is we are going to study the interaction between a single mode field and this two-level system. Okay, so with the advanced technology now it is possible to study the interaction between a two-level system and a single mode field, and the model describing the simple model describing the interaction between this two-level system and the single mode field is called Jaynes Cummings model. Okay, so in order to start with the Jaynes Cummings model, we have to start with the Hamiltonian of the atom field interaction. Okay, now before going to that, we can give a schematic representation of Jaynes Cummings system. Okay, so in Jaynes Cummings system we'll have a cavity. So the cavity walls, these are cavity walls. Okay, so we have cavity walls, and inside the cavity the field is confined, and as well as there is some two-level atom inside. Okay, you can see a two-level atom. Okay, so these two lines represent two energy levels of this two-level atom, in which the transition between these two levels are allowed. Okay, the lower state I denoted by symbol Kg stands for ground, and the upper state I represented by symbol Kd E stand for the excited. So the energy corresponding to the ground state I can denote by symbol Eg, and excited state I can represent by symbol Ee. So this is a schematic representation of Jaynes Cummings model. Okay, so in order to derive the Hamiltonian for the system, we have to start with the atom field interaction. Okay, so the atom field interaction Hamiltonian, we have seen that it can be split into two parts. The first one is the free Hamiltonian of atom plus the free Hamiltonian of the field plus the interaction between the atom and field. Okay, so H0 will have two parts, one the Hamiltonian of the free Hamiltonian of the atom plus the Hamiltonian of the field. And the Hamiltonian of the atom, it is very simple. It is we can write p square by 2m, the kinetic part plus the potential V of r. Okay, so that is we already know the Hamiltonian of single atom. And Hamiltonian of single mode field I can write a dagger a plus half h cross omega, where omega is the frequency of the field, and the interaction between the field and the atom can be as minus d dot E. It is in the dipole approximation. This d is called dipole moment and E is the electric field. Okay, so suppose the electric field is confined in a one-dimensional cavity, so that is the assumptions that you are making. Okay, if it is confined in the one-dimensional cavity, with the cavity become the cavity has the boundary at z equal to 0 and z equal to L, then the field must be 0 at both these boundaries at z equal to 0 as well as at z equal to L. So then the electric field operator I can write as square root of h cross omega by epsilon 0 v a plus a dagger sine of kz. Then we have written a vector here. This vector represent the direction of polarization. Okay, so this vector E is a polarization, vector small e is the polarization direction of the field. Okay, so and then the dipole moment operator can be written as minus q into the position vector operator. The q is a charge and r is the position vector operator. Okay, so finally the interaction Hamiltonian H prime I can write as minus d dot E, and if you substitute both d and d, okay, I can give the different numbers or for all these terms. So let this can be we are starting from here. This can be equation number 1, it may be 2, then 3, 4, 5, and the electric field definition is 6, dipole moment is 7. Okay, so using 6 and 7 I can write my equation number 5. So which gives h prime is equal to minus d dot t, and I can simplify this expression. H prime I can write as d into g into a plus a dagger. So g is minus square root of h cross omega by epsilon 0 v sine of kz, and this operator d is the dipole moment operator dot the polarization vector. Okay, so that is the definition of d. So this can be equation number 8, equation number 9, and equation number 10. Okay, so we are more interested in the equation number 8. Okay, so we'll try to change the equation number 8 soon. Okay, so in order to change the form of equation number 8, we have to introduce a few operators. So first we are introducing the operator called the excitation operator of atom, and that is denoted by symbol sigma plus, which is the outer product Eg. Okay, so what is the action of the sigma plus? So we know that in case of atom there are two possible state. One is the ground state and other one is excited state. So if you act sigma plus on excited state, what you will get? So sigma plus acting on excited state, they to become E into Ge. Now what is the inner product between G and E? The G and E are the eigenstate corresponding to different energy eigenvalues. So obviously they must be orthogonal to each other, and therefore this would be equal to 0. So this is 0. Okay, so sigma plus acting on excited state is 0, and whereas what is the action of sigma plus acting on G? Again, you can substitute sigma plus is nothing but E into G, and acting on G, so you'll get inner product Gg, inner product Gg would be 1, so this would be equal to E. So the action of sigma plus acting on G would be E. So that means if sigma plus act on ground state, the state will become excited, and sigma plus acting on excited state, it becomes 0. So that is why the sigma plus is called the excitation operator. It excites the atom from ground state to the excited state. Okay, so similarly I can define de-excitation operator or lowering operator, and it is defined by symbol sigma minus. It is simply the Hermitian conjugate of sigma plus. So I can write this outer product Ge, and you can verify that sigma minus acting on E will become G. That is, if sigma minus acting on excited state, it will become the ground state, and whereas sigma minus acting on ground state becomes 0. So you can verify yourself this is correct. Okay, so after that we are going to introduce another important operator called inversion operator. Inversion operator I am going to denote by symbol sigma z. Okay, so sigma z is the outer product EE minus outer product GG. Okay, outer product EE minus outer product GG. Okay, so I am not going to discuss what is the action of it, we will see it later. Okay, what is the importance of this sigma z operator? Okay, so I have defined three operators: sigma plus, sigma minus, and sigma z. So this can be equation number 11, 12, and 13. And we can show that this equation number 11, 12, 13, it obeys the Polish algebra. Okay, so that means if you find the commutator between sigma plus and sigma minus, you will get sigma z, and sigma z, sigma plus commutator will be 2 sigma plus, and sigma z sigma minus commutator will be 2 sigma minus. Okay, I can show one of it. After that you can do it for the remaining things. Okay, so let us begin with sigma plus sigma minus commutator. It is basically sigma plus into sigma minus minus sigma minus sigma plus. Now what is sigma plus? So sigma plus is E G, and what is sigma minus? It is G E minus, and what is sigma minus? It is G E, and sigma plus is E G. Okay, so here you will get an inner product GG, here you will get inner product EE. So the inner product GG would become 1, so this would be simply the outer product EE minus this would be the outer product G, and this is nothing but your sigma Z. Okay, so this is proved. So the commutator between sigma plus and sigma minus would give the inversion operator. So excitation the commutation between the excitation would give the inversion operator. Okay, so the other two things you can do it yourself. Okay, now if you look at the dipole operator, so remember our aim is to change the expression for H prime. Okay, so that is my aim. I want to rewrite H prime in terms of the annihilation creation operators or the excitation de-excitation operators. Okay, now how will you write, how can you represent an operator in terms of a basis? So it's called the spectrum theorem. We can expand it. Okay, so if you consider a dipole operator, the dipole operator is basically D dot E, this minus Q R dot E. So this, it contains R, it has a position vector R. So therefore the dipole operator has a single parity. Okay, so that you keep in your mind. Now you can use a completeness theorem, and you can express D, you can expand D in terms of the basis as the sum of product of outer products. Okay, so D can be written as DEE okay, plus DGE plus DEG and DGG. So this kind of representation you might have studied in the mathematical formulation of quantum mechanics. It is how to represent an operator in terms of the outer product. It is not a very difficult task, so you can do it very easily. Suppose if you have some operator D, then D can be written as some identity operator into D into I. Now this identity operator you can write as sum of outer product of basis vectors. So this identity operator, here we have two basis vectors, one is EE plus GG, then D, and we'll have another set of identity EE plus GG. Okay, so if you look at this, you will get a total of 4 terms. The first term is represented as DE, outer product EE. What is DEE? DEE is nothing but the inner product EDE. So if you expand this, the first term would be inner product EDE, then outer product EE. So this term have denoted by symbol DEE here. Similarly, I can find out what is my DGE and DEG and DGG. So all these, so these elements we usually call matrix elements. So I can find the matrix elements, all these matrix elements, DE, DGE, DEG and DGG. Okay, so it is possible to represent any operator in this matrix form if you have a basis. Okay, so if it is a discrete basis, it will be a finite matrix. If it is a infinite basis, it will be an infinite matrix. That's all. Okay, so what is your DEE? DE, or in general DIJ, the matrix element, it is the inner product ith basis into D into jth basis. Okay, but the D is having the odd parity. So if you look at the matrix element DGG, so that is the inner product GDE, the D is having the odd parity. So since D is having odd parity, this inner product will become 0, and as well as the inner product EDE would also become 0. That means the two of this matrix element will directly go to 0. The first one is DEE will go to 0 and DGG will go to 0. So that means you will have only two matrix elements. One is DGEGE plus DEGEG. Okay, so therefore your dipole moment operator I can write as DGEGE plus DEGEG. Now what is GE? GE is nothing but your sigma minus, and EG here your sigma plus. Now this DEG or DGE, I am hereafter I am going to mean by symbol D, and since it is a real number, the DG and DEG both would be the same. Okay, so finally your dipole moment operator again similarly written as D into sigma minus plus sigma plus. Okay, because this is your sigma minus and this is your sigma plus operator. Okay, de-excitation and excitation operator. Okay, so that would be the next equation number. So this can be, okay, let in the time being this can be as 14, 15, 16. We are not going to use this for now, but let us keep it with some equation numbers. Okay, and let this would be your equation number 17. Now you can use your equation number 17 in the definition of in the previous expression of h prime, and we have written the h prime as equation number 8. So use equation number 17 in 8. That would give h prime equal to dg a plus a dagger, that is this operator d can be written as d into sigma minus plus sigma plus, then a plus a dagger. Now this dg, now I am going to change the notation. So I am going to introduce another constant called lambda. Lambda is defined as dg by h cross. Okay, so therefore this dg can be written as h cross lambda. So h cross lambda into sigma minus plus sigma plus times a plus a dagger. So this can be equation number 18. Okay, so similarly we can write the free part of the Hamiltonian. So if you look at the HA, the atomic Hamiltonian, so atomic Hamiltonian again I can represent in terms of the matrix element. Okay, here it is only two-dimensional basis, only two states are possible there, E and G. So HA can be expanded as GHAG outer product GG, GHAE outer product GE, etc. So there will be 4 terms. Now here 2 of these terms would become 0. So which of these terms become 0? Okay, so in order to identify it, so let us denote HA acting on ground state would be EG into ground state. Remember, EG is the energy of ground, and HA acting on excited would be EE excited. Okay, so HA acting on G would give EGG. So then you will get EGG. Then HA acting on E would be EEE, and HA acting on G, EGG, HA acting on EEE. So total 4 terms are there. Okay, now this EG, EE are just numbers. I can take it outside from the inner product. So then what will happen? If you take this EE outside, it will become the inner product between G and E, and that would be 0. So this term would cancel, and as well as this term would also become 0. So finally we will get only 2 terms. One is EG outer product GG plus EE outer product EE. Okay, now I am going to denote the values for EG and EE. Okay, for that, so our textbook, which is I am following the introduction to quantum optics by Gary and Knight. Okay, so in that textbook they have chosen the central portion of these two energy level as 0, and the transition frequency denoted by symbol omega 0. So that means the energy difference between the ground state and the excited level denoted by symbol h cross omega 0, and therefore the ground energy is denoted by symbol minus h cross omega 0 by 2, and the excited is denoted by symbol plus h cross omega 0 by 2. So if you are following some other textbook, then some textbook takes the lower state as energy 0 and upper state as plus h cross omega 0. So there are different conventions followed by different textbook. So here I have followed a textbook by the Christopher Gurry and Peter Knight. Okay, so then your the Hamiltonian for the atom I can write as h cross omega 0 by 2 Gg minus Ee, and this operator we have already seen earlier, we already defined earlier. We have given the name for it as sigma z, and it is called the inversion operator. Okay, so therefore the Hamiltonian of the free Hamiltonian of the atom is simply h cross omega 0 by 2 into sigma z, and this can be my equation number 19. Now finally, the Hamiltonian of the field. The Hamiltonian of the field we already know, it is A dagger A plus half h cross omega. Here half h cross omega is simply the background energy, or it is called 0 point energy, and it would be present always. Okay, and it may not give the dynamics, it may not contribute to new dynamics to the system. So therefore, in order to simplify the situation, we are going to ignore the term of the 0 point energy. So by ignoring or by dropping that 0 point energy term, the field, the Hamiltonian of the field, I can write as A dagger A times h cross omega, and this can be the equation number 20. Okay, now we have written the Hamiltonian, the free Hamiltonian of atom and free Hamiltonian of the field, and plus the interaction Hamiltonian. So by combining all these three things, I can write the total Hamiltonian of the atom field interaction between the single mode field and the atom. Okay, so remember here I have introduced only the single mode. If multi-mode fields are present, instead of one A dagger A, there will be many A dagger A. So you may have to introduce A1 dagger A1 plus A2 dagger A2 plus etc. And different mode can have different frequencies. So if it is multi-mode, the HF would be sum over n or sum over I. AI dagger AI into h cross omega I. So that would be the multi-mode Hamiltonian if you ignore the 0 point energy. Okay, so here for the time being we have considered only the single mode field. Okay, so that's why this is the very simplified the model of the atom field interaction. So we are considering the atom is just two level atom. We are not including the multiple levels of the more than two levels. Okay, we are limited to only two levels. That is the minimum possible energy level for the atoms in order to ensure the transition. And we are assuming the field is single mode. Okay, that is on single frequency is present in the field. Okay, so by combining all these, we can write the total Hamiltonian. The total Hamiltonian has now 3 times HA, HF plus HI. So from all the previous equation, you can just substitute it. Okay, so the atomic Hamiltonian, the field Hamiltonian of single mode. So this is for two level atom, and this is for single mode field, and this is the interaction. Okay, now again you can further simplify this Hamiltonian by ignoring few terms. Okay, so in order for that we have to just think about what is the last term looks like. So the last term is containing actually 4 terms, the interaction term. So there will be sigma plus, if you remove this bracket, there will be 4 terms. One is sigma plus A, the second one is sigma plus A dagger, sigma minus A, and sigma minus A dagger. Now what is the meaning of sigma plus and sigma minus? So remember, sigma plus and sigma minus is the excitation and de-excitation of atom. So it means if you act sigma plus on atom, the atom may excite, and sigma minus on atom, the atom may de-excite. And A dagger is the annihilation or creation of photon. That is, the action of action of A decreases the number of photon, and action of A dagger increases the number of photon. Okay, so then we can look at what is the meaning of the combined term. Okay, so if you look at sigma plus A, so sigma plus corresponding to excitation and A corresponding to annihilation. So sigma plus A means the excitation of atom with photon annihilation. So we can excite atom by removing a photon. So that is what is meant by sigma plus A. And what is the meaning of sigma plus A dagger? It is excitation of atom with photon creation. So there is the atom is going to excite plus a photon is being created. And sigma minus A, there is de-excitation of atom and photon being annihilated. Okay, so by removing a photon, the atom is going to de-excite. And sigma minus A dagger, the atom de-excites plus a photon is created. Okay, now if you look at these four processes, so some of these processes are not going to conserve energy. So which of these processes are not going to conserve energy? Okay, so just think about it. Suppose if there is no external force or there is no external energy on the system, okay, so you have a two-level atom. So atom either can be in ground state or in excited state, and you have some field here which is confined in some cavity. Okay, so and suppose this atom is already in excited state, it may de-excite. So de-excitation is corresponding to sigma minus, and during de-excitation it may emit a photon. So emitting creation of photon is basically a dagger. So this is a possible process. So by de-exciting an atom, a photon may be created. Okay. Now similarly, what is its opposite process? So consider cavity with some field inside and two level atom is a ground one excited. Suppose the atom is already in ground state, so it can excite. Okay, so the excitation is basically sigma plus, but by on excitation the photon must annihilate. Okay, the photon must vanish, and the vanishing of photon is basically represented by symbol A. So sigma plus A is a possible term if there is no external driving. So in the absence of external driving, basically you only two possible term would be available. One is sigma minus A dagger and sigma plus A. What about the other two terms? What the other two term means? It is sigma plus A dagger means by exciting a photon is going to create. So that is not the energy conserving term. Okay, so whenever the atom is going to excite, it absorbs photon. Okay, it may not emit a photon. That is a usual case. Okay, so there can be that kind of process as well. That is while the atom excites, there can be emission of photon. Okay, for the time being we are not going to consider it. Okay, because there is a possibility of the energy uncertainty and so on. There are possibility that the energy conservation may violate for a small amount of time. That is possible. So even though the atom excites, it may emit a photon. So that is possible. Okay, but if you're not considering all those facts, then if you're looking at the simplified way, then the sigma plus A dagger and sigma minus A are the non energy conserving terms. Okay, so that is in the absence of the external driving, the process number 2 and process number 3 are not consistent with energy conservation, but the other two are consistent. And that means whenever atom de-excite, it can emit a photon, that is sigma minus A dagger, that is possible. And the atom, whenever the atom excites, it can annihilate a photon, sigma plus A is also a possible term. Okay, so therefore we can drop the non-energy conserving terms, that is from 2 and 3. So if you drop those two terms, then the Hamiltonian will become half h cross omega 0 sigma z plus h cross omega A dagger A plus h cross lambda sigma plus A sigma minus A. So remember, this is corresponding to a two-level atom. Okay, and this is corresponding to a single mode field. Now remember, this need not be atom, or it can be any system which is having two levels. And sigma plus A is corresponding to excitation with photon annihilation, and this is de-excitation with photon creation. Okay, so this is the final Hamiltonian. Okay, so what was the equation number for the previous Hamiltonian? So that this can be equation number 21, and from equation number 21, so by dropping this equation number 21 will take this form, and this can be equation number 22. So the system which follows this Hamiltonian is called the Jaynes-Cummings Hamiltonian, or the Jaynes-Cummings system, and the corresponding this Hamiltonian is called the Jaynes-Cummings Hamiltonian. And this is the simplified model describing the atom field interaction. So why it is the simplified model? The reason is here we have considered a simplified model for the field. The field is considered to be a single mode, and the atom is again a simplified thing. The atom, we have taken only two possible level for the atom. We are going to consider the transition between only two energy levels, and we have also removed the non-energy conserving terms. And the approximation for removing the non-energy conserving terms is called rotating wave approximation. So this approximation is called rotating wave approximation, is simply called RWA. Okay, so if you summarize the JCM, it is the simplest quantum mechanical model for atom field interaction. And why it is simplest? Here we are considering atom only two levels, and the field we have considered only single mode field, and with rotating wave approximation. It is ignoring non-energy conserving term. So actually these are starting points to study the quantum optics, the interaction between a quantized light and a quantum system. And once you start with this, you can expand more complexity to the system. You can add multiple atoms and multimode fields. So different possible levels of complexity you can add. You can introduce a nonlinear interaction. So there are many possibilities for the extension of this Jaynes-Cummings model. So that is why this Jaynes-Cummings model is sometimes it is also called the hydrogen atom in quantum optics, because in quantum mechanics the hydrogen atom is a starting point. From that we can build to the bigger atoms and molecules, etc. So similarly, the JCM, the Jaynes-Cummings model, is the most simplified and most compact model and most easy model to study completely. You can get analytical solution of this. Okay. And moreover, it is possible to achieve this kind of system in laboratories as well, because with the current technology we can achieve all these conditions. Okay, so with this I am going to wind up this lecture. Okay, so in the next lecture what I will going to do is I will going to discuss the dynamics of Jaynes-Cummings systems. Okay, so thank you for watching this video. We'll see you later with the new lecture. Thank you.